Okay, welcome back to another episode with a Sharp Education. We're going to be building on our logistic regression output again. And just like with linear regression, there's a couple steps we should take to understand what's going on with each of our outputs before we just trust them altogether. So, a logistic regression output could just give you this, what we're looking at now, and you will see like a 54% accuracy, and that'll be it. But that's not very informative. So, just like a linear regression output with no charts or no deeper dive into what's going on underneath the surface, the surface level responses that you get from these outputs are not super helpful. So today we're going to be looking at the confusion matrix. Now, what is a confusion matrix? Simply put, it's just how confused the logistic regression model is and what is confusing it. So as we know that we can get a 1 or a 0 as an output from our logistic regression model because we have defined our target variable to be a 1 or a 0 depending on whether or not the close price is higher or lower in the set amount of shifts that we want our look ahead window to be. So if we're on the hourly chart and we chose our shift to be 5, we just want a 1 or 0 depending on prices are higher or lower 5 hours from now. Now today we're looking at the confusion matrix, and confusion matrix is a chart that has 4 sections. So there's 2 sections for trues and false. 2 sections for true, 2 sections for false. There are false positives, false negatives, true positives, and true negatives. No. So we have true positives and false positives, and we also have true negatives and false negatives. So what do we want? We want to be minimizing the false positives and false negatives. But what we're going to be looking at is where the majority of our responses are and where the majority of our errors are coming from. Like, is it really not doing a good job of identifying negative outcomes, or is it just always identifying positive outcomes and that's where our accuracy is coming from? The confusion matrix elucidates a lot of what is going on with our output in the first place. So let's just get right into that. We're going to be importing a couple new packages today. We use stats models for the outputs that we're looking at now, but we're also going to be importing the confusion matrix from Scikit-Learn. So from Scikit-Learn, import confusion matrix, Scikit-Learn dot metrics. We're going to import confusion matrix. And if you don't have Scikit-Learn, you need to pip install Scikit-Learn, I think is how you do it. And it's going to say requirement already satisfied for me. And we're also going to be installing Seaborn. So pip install Seaborn. And I, again, already have that. So we're going to be doing import Seaborn as SNS. Seaborn is what's going to create our nice, beautiful confusion matrix plot. The matplotlib default functions, which you've seen me use, are not very beautiful at all. But a nice, pretty looking confusion matrix it's just good to look at. So we're going to have that. We also need to update our regression output to be prepared for showing the differences between predicted values and actual values. So we have this whole response from our regression analysis that we've already conducted, but now we need to build on it. We need to create our predicted y values, and those are going to be extensions of the probability associated with those predictions. So when we run the logistic regression model on our features, so y pred probability, y pred prob is going to equal model.predict and the x with constant we've already defined. Model which we have dot predict, and we want to predict the x with our constant added to it, so just shifted for whatever the y-intercept is. And then from there, the y prediction, or just the standard y, is going to be whether or not our predicted probability is greater than 0.5. And you remember from last episode, our sigmoid activation function, or just our sigmoid function, compresses all of our responses between 0 and 1. If it's closer to 1 than it is to 0, then it's a 1. If it's closer to 0 than it is to 1, then it's a 0. Greater than 0.5. So y pred is just going to be y pred prob is greater than 0.5. That's going to be our threshold. And we're going to change this into an intercept. So let's put this in parentheses and do as type int. As type, make a little modification, intercept. Perfect. So what are we going to do with this y prediction? We already have model summary printed out. So after that, after we print our model summary, I want to do a couple more things. I want to make a column specifically for our predicted values. And I'm also going to, we already have our target variable, which is what it actually should be. So I'm going to do data frame predicted is going to equal y pred. So data frame predicted prediction is going to equal y pred. So y pred is a list of responses, either 0 or 1, that are, it's going to be the same exact length as our data frame. So this is going to modify our data frame when we generate the regression output. And I'm going to take a look at our data frame by calling data frame equals main, getting rid of this, and then let's make another code just to look at our data frame. Perfect. So we have predictions that are all equal to 1. And if you're new to this space, which I hope you are, or which I assume you are, that's a little funny. They're all 1. Why is that? Why are they all 1? Any ideas? Well, I know, and I'm actually not going to tell you yet. I'm going to let you think on that while we make this confusion matrix. So let's just start. I mean, we can do data frame prediction dot values, value counts. And, oh, okay. So the vast majority of predictions are 1. And there's only 142 predicted negative days when our feature or our x variables are open, high, low, close, and volume. So based on the features we've fed this model, really unlikely to predict a down day, but it does exist. So let's dive a little closer into this. Like, what is it predicting? When is it predicting these things? This is what the confusion matrix teaches you how to do. This is a really good graphical representation of the logistic regression output. So we're going to define create, add, confusion matrix to the data frame. And I think that's all we need. Yeah. So confusion matrix, or CM, is going to equal our confusion matrix just from the response that we created with our generate regression output function. So confusion matrix, and we're going to get data frame target, because that's our default y values, and data frame prediction, because you're supposed to do a confusion matrix between the actual values and the predicted values. And the labels are just going to be down or up. Down is going to be 0 and up is going to be 1. So let's do this. Labels equals a list of down, which is 0, and comma separated, or up, which is 1. Perfect. Now, our confusion matrix data frame is going to be a pandas data frame of our confusion matrix with a couple extra specifications. So I'm just going to write it down and explain it for you this way. Doing this step here makes it readable by Seaborn. Data frame equals pandas pd dot data frame of our confusion matrix, and the index is going to be the labels, and the columns are also going to be the labels. So index labels, labels, columns, also labels. So why are the index and labels the same thing? Well, it's because they're both trying to assess whether or not we're getting a true positive or a false positive and a true negative and a false negative on both axes. The only difference is we're using predicted versus actual values. So it's the same, we're looking at the same thing just for two different versions of that target variable, predicted target and actual target. So the labels and index are exactly the same. And I might just be saying way too much before showing you what we're actually looking at. So I'm just going to finish writing the script for this matrix, and then I'll walk you through what I do at the end here. So let's make a plt.figure, just like always, and then SNS is going to be a heat map of the confusion matrix data frame. So let's get a title and an X label and a Y label, and then just show it. So plt.title, plt.x label, and plt.y label. Perfect. So the title is just going to be confusion matrix, but I could get more creative with that later. Confusion matrix for now is going to do it. Confusion matrix. The X label, X is always going to be predicted and Y is the actual. So we're going to do predicted, Y is the actual. Okay, and that should be it. Just return this. And I'm going to add this to our main function. So data frame is now going to be add confusion matrix to the data frame. So it actually looks like this is white. These 72 and 71 are white. But if you look really closely, really closely, I guess that doesn't really help. This is actually really light blue. And if you look at our scale, if it's less than 500, then it becomes really close to white. So this is not a super great plot. I might change the output from blues. No, I'm gonna leave it as blue, and I can run with this. So it's almost always predicting up. Fortunately, there are more true ups than there are false ups. So the actual versus predicted. So when the actual predicts down and it actually goes up, that happens less often when the actual predicts up and it actually goes up. You can tell this because it gets darker as the number increases and it gets lighter as the number decreases. But you can see that when it predicts down or up, actually, the predicted value, when it predicts up or down, when it predicts down, it ends up being about a 50-50 split. But when it predicts up, it's accurate more often than it's inaccurate. So what's going on? This is run on daily data for the S&P 500. So the S&P 500, over the course of its 30-year time frame that we have for free with Yahoo Finance, goes up 54% of the time. And regression is able to understand that. It just knows, like, okay, no matter what happens here, it goes up. No matter what happens here, it ends up being a 1. This tends to be a 1. So what ends up happening is almost always, unless you can find a statistically significant variable that suggests otherwise, that suggests it knows when prices are going to come back down, the vast majority of predictions are going to be up. Okay, so what if we, instead of testing the open, high, low, close, and volume prices, we brought in some of our technical indicators from before. So let's take a look at the MACD indicator. Control C, Control V, great. And we also need to load in those global variables. Control C, Control V, perfect. So that should be everything we want. Our strategy is going to be it's going to be just volume and MACD. Just two indicators, volume and MACD, hist, lowercase h, hist. Okay, now we have different indicators here. Let's see if that changes our confusion matrix. Because I did not add the MACD to our main function. So before we add the target, let's go data frame equals add the MACD to the data frame. Try it again. So our constant is 0.068. Volume, this is the correlation coefficient here, and the correlation coefficient for the MACD. So what are we doing? We are taking the multiplicative factor of the MACD histogram with its correlation coefficient and the volume with its correlation coefficient. We are adding the constant, and then we are adding this function, or the output of this result, to the sigmoid function, which then responds with a large list of outputs between 0 and 1. I'm actually going to plot a histogram of our y-pred probability. Print y-pred prob. This might be informative. No, I'll do plt.hist. plt.histogram of y-pred prob. And then plt.title. And that's going to be a range from between 0 and 1. So let's do plt.figure, plt.figure. And that'll be it. We're going to make that slight adjustment so I can show you guys what's going on. Oh, we're gonna add more bins too. Do bins equals 50. Bins equals 50. Okay. So this is the distribution of predictions. And remember, our cutoff is 0.5. Most of our predictions are around 0.51, 0.52. So the vast majority of our predictions are going to be 1. And this small section that happens below 0.5 is going to be a 0. Now the confusion matrix tells us which one of these predictions that are above 1 are accurate and which ones of these predictions that are below 0.5 are accurate as well. So of those that were above 1, which you can see is the vast majority, predicted up is a significantly darker shade of blue than these light blues over here. They were more accurate than inaccurate because, generally speaking, prices go up over time. This is no longer the daily data frame. This is the 1 minutely data frame on GTLS. But there are more up candles than down candles throughout the course of this study. I'm actually going to do a plot of close prices so we can show you guys what the environment we're looking at over the course of our study. So plt.plot data frame close. Right. So you can see that more often than not, prices went up than they did down. So of course, when we provide two pretty non-significant indicators, which we can see based on our p-values, these are not really important variables. They don't provide a statistically significant relationship or any insights that are extremely important. So generally speaking, it's just going to guess whichever happened most often. So it usually went up. So let's see if we can find a stock that didn't usually go up. And I'm going to add this to the list of plots we see before we look at our confusion matrix. Control X. This is going to be plt.figure. And we're going to add this line to the MACD as well because we are now putting this up. Okay. And we're going to make a title for it as well. plt.title is going to be price movements for, and then ticker. We can do that lowercase, over study, during study. Quotation mark, F string. So we're going to now have a plot that gives a pretty good synopsis of what we're looking at. So the price movements for GTLS over the 1 minute study generally go up. This is the MACD histogram. I'm going to get rid of that. Don't want it anymore. Gone. We know what it looks like. And then this is the distribution of logistic predictions, and it starts off with the vast majority being greater than 0.5. A perfect logistic regression output is centered around 0.5, but that's really rare because most of the data sets you're going to work with are skewed to one direction. And because of this skew of upwards going prices, our distribution is above 0.5, and the vast majority of our predictions are 1. Now, let's see if we can find a minutely price chart that hasn't gone up recently. Let's look at Lululemon. I think they've had some negative news recently. Okay. I don't really like this plot. Again, it's still generally greater. Let's do 1 hourly of Lulu. I think that will show a different result. Yeah, so with Lulu, prices generally go down. Or they've been pretty flat, but down. And this is, the opposite case. The majority of our predictions are below 0.5, just because we're working with statistically non-significant variables. If these are not going to impact your decisions, then the best the model can do is create a loss minimization outlook that just gives you the majority of the time a 0 or 1. So unless you're working with statistically significant valid variables, which again are not the technical indicators that we've covered, by the way, which should be interesting to you, you are not going to find a confusion matrix that is really beautiful. And what does a beautiful confusion matrix look like? It looks like a really dark square here and a really dark square here and a really light square here and a really light square here. So that means that when it predicts up, it actually goes up. And when it predicts down, it actually goes down. And then the false positives and false negatives rarely occur. These confusion matrix charts are super useful. And once you understand what a good one looks like, or once you see one, then you have potentially the good foundation to build an effective trading strategy. But again, the hard part is finding a good one. The easy part is following it. Emotions, discipline, trading, patience, it's all made up to make the standard approach to trading, or the TikTok, Instagram, social media approach to trading seem like something difficult, but it's not. This is the difficult part, and you are sticking with it. So congratulations. I know these episodes are a bit more boring, but they lay the groundwork for really exciting stuff. So when we start doing exciting strategies, you're not going to be like, what the hell? How did he get to that conclusion? I don't understand what any of this means, but you're sticking with the boring stuff. So congratulations. This is what is important. This is how you know you're moving in the right direction in trading. Before we get to using this, just a full-scale episode of me using the logistic regression function that we make, I'm going to be talking about area under the curve. And that's a really similar output to the confusion matrix, but it's commonly used and something you should understand if you're going to be in the regression analysis trading space. So, once again, thanks for sticking around. I appreciate you being here. Leave a comment that lets me know that I'm not going insane and talking to myself. Just say, thanks, cool confusion matrix, or something. I don't know. And then that's it. Until next time, stay sharp.